So I want you to try one, right? So I want you to try one on here, okay? And so this is what I want you to try. And so example number 4, I think. So f of x is your arctangent x. So what is the derivative of arctangent x? It's 1 over x squared plus 1, or 1 plus x squared, right? So let me write it as 1 plus x squared. And this was problem number 1, right? So this is the first problem we did today. So now you want to integrate that and get to this part. So see if you can figure this one out, right? So we already did the first part, right? So this was problem number 1, right? So this is problem 1. So we already did that one, right? So see if you can actually integrate it and get your answer. So let me pause the recording. All right, so let's see if you get the same answer as I did, okay, or I will. So recall the power series for this one from the previous problem, or at least problem number 1 was -1 to the n, x to the 2n power. And then now integrate that, right? So you're going to go ahead and integrate it to get back the original function, right? Because you took the derivative to get here, then you have to go back. And so it's n equals 0 to infinity. Again, the -1 is a constant as far as integration is concerned because you're integrating with respect to x, right? So let me actually put that over there. So we're integrating with respect to x, right? That's what we're doing, okay? So x is our variable. And so when we integrate, we'll have -1 to the n. So it's a power rule all the time, right? Because it's a polynomial. So it's a polynomial. That's what a powered series is. And so add 1 to the power. So it would be x to the 2n plus 1 all over divide by the new power, which is 2n plus 1. Okay. And then, right, a plus c, right? It's always a plus c on there. But then you have to evaluate, right? So again, the easiest way to do this is to plug in 0. So if I plug in 0 to arctangent, and so arctangent of 0 is 0. So again, it's 0. So which means when I plug in 0 for x, all of these polynomials are going to give me 0. So for the whole thing to equal to the original, c has to be 0 again, which means my power series is from n equals 0 to infinity, -1, x to the 2n plus 1 over 2n plus 1. And there is your answer. Okay. Any questions on that? So the question is, what happens if the function is not 0? Well, the nice thing about um, plugging in 0 is because your power series are all going to be 0, right? Because there's an x there for every one of them. So when you plug in 0 to a polynomial with all x's on it, the answer would be 0 except for the c part. So which means c is going to end up equal to whatever the value of your function is. So if, for example, if you plug in 0 to your function and the answer is 5, then that means c is going to have to be 5. And then just simply plug that in on there. I would actually put the 5 in front, but that would be your C on the problem. Anything else? Okay. So now, okay, the next question becomes, well, what happens if I have a function that is nowhere related to a rational function, right? So the arctangent, the derivative was a rational function. So that's why we were able to use the geometric series. Same thing with the natural log, right? So derivative of natural log was 1 over. So you end up getting a rational function at the end. So the question is, what happens if your f of x is nowhere related um, to a rational function? So for example, how do we do it? So what if f of x is e to the x, right? Because derivative of e to the x is e to the x. Well, there's nowhere on there's a rational function on it. So now what do you do, or how do you represent e to the x as a power series? And so this is where Taylor and Maclaurin series sort of comes in. Okay, and so essentially those two sort of developed a method on a way to essentially um, find a power series representation for any function. Okay, so now to do this or to explain, okay, how this is done, okay, um, I have to derive where it comes from. Okay, but there's a question. Oh, sorry, that should still be there. Thank you. The n should still be there. Okay, I just didn't write it somehow. Okay, but it's still there. Okay. Anything else? So there's still an n power on the negative one. Okay. Anything else? Okay. All right. So I do want to derive, okay, your Maclaurin and Taylor series. Now the difference between the two is Taylor is more of the generic one. So this is where it's centered at A. Maclaurin, the center is 0, right? So let me write that out. So Taylor is when the center is A, and this one is where the center is 0. So that's the difference between the two. Okay. And so let's do the centered one where it's the Taylor one. And so essentially, this is what we want to get, right? So essentially, we want to have f of x to equal a power series, right? So from n equals 0 to infinity of c sub n x minus a to the n power. All right, so now what I want to do right now is write out the first few terms of this, right? So we want f of x to be equal to the following. So c sub 0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed plus c4 x minus a to the fourth plus dot dot dot. All right, and so now the idea here is for any function, right, to represent as a power series, the key part is figuring out what the coefficients are going to be, right? So what are they going to be for each one of your functions? And so now to do this, we can impose, and really that's what Taylor and Maclaurin did, was they imposed conditions um, on what your function or your f of x or your polynomial is going to satisfy in terms of its function, right? So for the first one, right, so the first condition, okay, is that if I plug in the center, the value should be the same. So meaning f of a should equal to p of a. So let's make p to be the polynomial, right? So we are talking about this being p of x, right? So the polynomial. So we want f of a to equal to p of a. So I want them to be equal when I plug them in. Okay. And so if I do that right now, right? So if I plug that in over here, so this would give me f of a. Okay. And if I plug in a onto the polynomial side, so plug it in for x. So this is a minus a, so that would be 0. A minus a, that would be 0. So all of these are 0 except for c naught. So that means c naught is equal to f of a. That a looks weird, so let me rewrite it. So f of a is c naught. Okay. All right, well, it's a function, and we're doing calculus, and so Taylor basically said, "Oh, I want to add some more conditions in terms of derivatives as well." So the next condition they applied was, "Oh, I want the first derivative to be equal." So meaning f prime of a must equal to p prime of a. Well, to do this, we have to take the derivative first. So the derivative, okay, of our polynomial, okay, and so this would be so p prime of x. So derivative of c naught, it's a constant, so that would be 0. Derivative of this, again, it's a power rule, so it's a power of 1. So derivative of this is just c1. And then this one would be 2c2 x minus a. And then this would be 3c3 x minus a squared plus 4c4 x minus a to the third power. And then now plugging it in, right? So plugging in a again, we get f prime of a is equal to, so if I plug it in here, again, all of these are going to be 0. And all I have left is 2c1. Oh, sorry, my bad. It's just c1 is equal to f prime of a. Okay. And so you keep doing it, right? So the next condition is I want the second derivative to equal. So f double prime of a to equal to p double prime of a. Okay. So p double prime. So c1 is constant. So this is 2c2. And then you just have a 1 power. So that's just 2c2. This would be plus 3 times 2. So the 2 will come down. And so you get 3 times 2 c3, right? And then this would be 4 times 3 c4 x minus a to the second power. And I forgot the x minus a. And again, plugging in a onto the polynomial, we get f double prime of a is equal to 2c2, which means c2 is f double prime of a all over 2. Let's do one more, okay? And then hopefully we can find a pattern here. And so we now want the third derivative. To equal each other. And so when we do, the third derivative will leave me with just this, and then everything else will have an a. So we'll have f triple prime of a is equal to 3 times 2 c3, which means c3 is f triple prime of a all over 3 times 2. And so you keep doing this. And we get the following. So C naught is equal to f of a. C1 is equal to f prime of a. C2 is equal to f double prime of a over 2. C3 is f triple prime of a over 3 times 2. So 3 times 2, if I put a 1 there, it's 3